Hello there. Welcome to this session on coverage metric overview. So as we have been discussing over this series of sessions, the point that verification is really a never-ending process. It keeps going on, and the time to end it is dependent upon like what's your quality criteria, right? And for different applications, you have different quality criteria. Like a medical application might have a very stringent quality criteria, whereas if let's say a particular chip is just being used in some toy, for example, right, then the quality criteria might be certainly very different. So depending on the application, we have different quality criteria, and the way you measure the quality is based on certain metrics. Okay, there are different metrics that are available which help you figure out how far have you progressed in verification, what is the quality of verification that has been completed, and coverage is one among them. So coverage as a metric plays one of the very important role in defining the progress of verification, as well as how much the design has been exercised, how much the features have been exercised, and that helps management make a decision that whether the design is ready for the tape out. Okay, so coverage is one of the key metric in being able to sign off a particular design. So as a part of this session, we will understand that how this metric is defined, and how it is generated, and how it can be utilized. So agenda for this session, we will first, as usual, we'll start off with our favorite question: why to do something, right? So we should always start off with why. So we'll look into it, that why we need to do coverage, and then we'll look at what is the coverage, and then what are the different types of coverage metric that are available. Predominantly there are two as of now. So we have code coverage and functional coverage. So we'll look at slightly one level deeper into what are these metrics and what do they help us understand, and then we'll close this session with the coverage closure flow, that how do you go about improving this particular metric and reach to a stage wherein you can now say that yeah, the design is ready, at least from the coverage metric point of view, right? And this whole session is going to, the idea of this session is that we lay foundation to go more deeper into the functional coverage eventually with the system Verilog cover group. So this is more of an introduction in a way, a slightly expanded scope, but this is an introduction to the session to get more deeper into the system Verilog cover group construct. So I never get tired by saying that verification is a never-ending process, and this makes it hard for us to answer question, are we done? All right. So how do you say that, since it's a never-ending process, how do you say that you're done? And the coverage is one of the key metric which is used to answer this particular question. So let's look into what is coverage. So coverage is a metric that tells us about the verification progress and completeness both. So during the process of execution, that is in our regression and debug phase, it guides us that week on week how much progress are we able to make. It is one of the metrics that helps us guide over there, and towards the end when we need to do the sign off, it helps us understand how much the design has been covered and how much the features have been covered, right? So it helps us understand both of them. So we can find out for example, which part of the RTL design has been exercised, how much each of the areas are exercised, as we have seen that certain areas are more important than other, and we need to know whether the important area has been exercised relatively more. So we can find that out, and which features are exercised. So features are independent of design, right? So sometimes it may not be possible to map the entire feature to one particular area. It could be spread out. So like features are generally captured using the functional coverage, which map to the requirement specification. So we can find out. So when I say coverage over here, I am like looking at it as a whole. That is the code coverage plus the functional coverage together. So we can find out which features are exercised, and it also becomes important to find out that the features are interacting with each other. because you might have multiple features, they might be working independently, but when things put together, do they work properly or not? Like for example, I might be taking a WhatsApp call, and if during that particular call, if a normal call comes, how does it behave? Or during the WhatsApp call, if a message comes, how does it behave? So cross feature interaction is a very important part of the verification. So whether that's happening or not, you can find it out using the coverage metrics. And then like there could be different configurations of the design that you need to exercise, whether all the configurations are exercised, whether the relevant features belonging to that particular configurations are exercised. All these things you can find out using the coverage metric. And coverage metric also helps us to prioritize the stimulus generation in the form of tests. And prioritization is very important part of verification, because we know that we can within, so that there is some time bound, right? There is a deadline that ultimately needs to be met, and within that deadline we may not be able to complete everything. Okay, this is the reality. So we may not be able to complete everything, but we need to complete the key features, and we need to make sure that the risk goes down, right? And there should not be any showstopper features which should be left out from the verification. So if I know coverage, then how much it is covered, then that helps me understand that, oh, this is the critical area, and this particular critical area does not have even enough coverage at this point of time, so we better focus on that particular area. So that's how it helps in the prioritization. And ultimate goal of all the metrics that we use in verification, be it coverage, be it bug number tracking, be it regression tracking, wherein we track how many tests have passed, failed, etc. So its ultimate goal is that we want to do the risk minimization, right? So since we cannot complete it, goal is that we at least do the risk minimization. Okay, let's understand what are the different types of coverage that are available. So this is the 4-quadrant diagram that I think I have picked it up from the coverage cookbook. So this 4-quadrant diagram, what's it trying to show us is that we have at the bottom we have two dimensions. We have implementation and the specification on the x-axis, and on the y-axis we have other two dimensions we have called explicit and implicit. So now what does the implementation mean is like when we do the functional coverage, or let me not say functional coverage, when you do any coverage, we are interested in two areas, right? So we have a requirement specification, and then that requirement specification has been transformed into a microarchitecture, and that microarchitecture we are implementing, right? That's what is the process of design. And what we need to understand is that for a given requirement specifications, there can be multiple possible microarchitectures that can be done. Okay, and then whatever some company has decided to do the microarchitecture in certain way, and that is what is getting verified, right? Ultimately that's what happens. So what we now need to cover is that we need to cover the requirement specification, which says, okay, we need to have so much of bandwidth, and we need to have so many ports, and we need to have so and so error handling capabilities, we need so much of reliability. So those are my high level requirements, and then how do I translate that into design is what is the implementation. So now in a way I need to make sure that I have verifying the requirements, and as well as I am verifying the implementation, right? So I need to when I need to verify both, because what happens is that when you take a particular requirements and then when you translate it into implementation, because of the way you implement it, there also creates additional cases that needs to be verified. For example, let's say I do buffer. I mean, like buffering is part of any bigger design. They do a lot of buffering. So now if that buffer, let's say I implement it in the granularity of 256 bytes, right? Then the 256 number becomes an important number. Okay, so now if I get a packet that's 257 bytes, then I need to allocate two buffers to store that particular packet. So so the multiplication factor of 256, there is some level of changes in the way the this particular architecture processes the packet. But if it was 512, it would have behaved certain differently. So now what I need to do is I need to pay attention to some of these factors, that how my microarchitecture has been designed, and because of that way of microarchitecting, there are some special cases that are coming out, and those special cases also needs to be covered. Okay, so now that is why we need to, so when I verify from both of those angles, I need to cover from both of the angles as well. So I need to cover from the specification angle, and I also, wherein I will just say I need to cover buffering, it has to buffer so much and stuff like that. And then when it comes to implementation, I will say, yeah, 256 bytes, if it's a multiplication of 256 bytes, 1 byte less than 256 bytes is a corner case for me, 1 byte less more than 256 bytes another important corner case for me. So I need to cover that particular implementation specific aspects, right? And then on the y-axis, implicit and explicit, what do they mean is that like the simulator tool is capable of generating certain coverage metrics on its own. You don't have to do anything, you just have to enable few flags, and based on that the tool itself is capable of looking at the design and generating certain metrics, code coverage metrics for example, automatically, right? So that's why it's called implicit, right? And then there are few things that you need to do explicitly, some metrics you need to do explicitly. So those there are two areas, right? So one is that if you have any implementation, that is you have a microarchitecture or design in the form of an RTL, and you want to cover certain microarchitectural aspects, like for example in FIFO we were saying, okay, you know, how much is the whether the FIFO has become full or not, for example, right? Or the both the push and pops are happening at the same time. So those might be a microarchitectural consideration. So for those you typically utilize the assertion based coverage, right? That you write properties which model the temporal relationship of a waveform, because the design works in the form of waveforms, right? So you can model waveforms using the properties, and those properties you can combine it with the cover directives and use it for covering the implementation specific aspects. Whereas when you have the specification, right, when you have requirement specifications, the requirement specification might be saying, okay, I need to cover all these packet types, these are the various sizes that I need to cover, and I should have a flow control in the middle. So all those things that are coming from the requirement, you typically cover using the combination of functional coverage and assertions. So it's a combination of both that you use. Now the difference between the implementation level assertions and the specification level assertion is typically you tend to do the specification level assertions only at the interface level. Alright, so between there are key interfaces at that signal level which is a spec defined. For example, when you go to PCI Express 5 and the digital core, they interact with an interface called pipe. Right now, pipe interface I could do pipe interface coverage I could do in the combination of both the functional coverage cover group as well as for the temporal relationships I can use the assertions as well. So those are requirements that are being covered using the assertions, as well as the microarchitecture implementation can also be used using the assertions, but additionally requirements where the stimulus is being generated from the test bench, and then the monitors are monitoring certain activities on the signal level and generating transactions, and using those transactions when you do the coverage you generally do it in the form of the functional coverage within the class based word. And then as we talked about the implicit for implementation, which is the RTL code coverage, it is all generated automatically. So within the code coverage there are multiple matrix, so we will look into it. And one interesting area is that for the requirement specification today there is no implicit coverage. Okay, so this all has to be done explicitly. So you need to take the specification and you need to define the coverage plan, and then you need to go ahead and implement either the assertion or the cover group based coverage, and then only when you run the regressions you get that specification driven coverage which comes all under explicit. The simulator cannot understand your requirement specifications and come up with the automatically cannot come up with the coverage. Okay, so that is not done yet, and this is the sort of an area of research that is ongoing. If this particular area interests you, I mean, drop me a message. So we have been doing something over here, and we can talk about it. See, the implicitly generated coverage metrics are very attractive because we don't have to do anything, and the simulator will generate it, and it will generate it based on already the code that I have written, right? So it's already telling me I have written a design which I am trying to verify, and the simulator is telling me how much of that particular code has been covered, right? Like which lines have been executed, which conditions have been met, and then which branches have been taken, which state machines have been exercised. It's telling me everything right now. we will get a question that why shouldn't I rely only on the code coverage metric, right? Why do I need to go for the additional like a functional coverage or assertion based coverage, wherein I need to invest extra effort in not only planning, but I also need to invest effort in implementing them, right? So why do I need to do that? Why is code coverage itself not sufficient, right? So why can't I say if I got 100% code coverage, why can't I say that it has met the 100% of functionality? There are a couple of points that we need to understand. First of all, when we have achieved the 100% code coverage, it doesn't mean that we have implemented everything that needs to be implemented in the requirements, right? Because I could have missed a particular feature, right? And there is no code for that. So now if my code shows 100% code coverage and I have not even implemented one particular feature, the simulator will not be able to tell that this particular feature has not been implemented. It's only going to look at what has been implemented, and within that implemented code, how much of it is being exercised by the test bench, right? That's what it is going to tell. So missing implementation I cannot detect with the help of the code coverage. And then there are two other things. So as a part of code coverage, your concurrent behavior, right? That is either within your particular block, you could have multiple concurrent blocks that are operational. Now, whether they were operational together at the same time is something that your code coverage metric will not be able to tell you. Okay, and same applies to the across multiple blocks. If you had multiple blocks, some of it you wanted it to be operational at the same time, then that is something that we cannot tell. And as we know, the parallelism is one of the very key important aspects of the hardware. Right now, that aspect is not covered by the code coverage, right? So sometimes you can infer it indirectly, but the problem is that there is so much of coverage data that whenever you have implicit metric generation, the simulators tend to generate so much amount of data that, and it is so large that it is very hard to understand a very specific aspect of something indirectly, unless and until it is explicitly being able to identify and call it out. Indirectly figuring something out is also error prone, and it is hard because of the total amount of data that gets generated. But bottom line is, there is nothing that the simulator officially provides you to tell you that whether something happened concurrently together. So that's not in the scope of the code coverage metric. So lack of concurrency is one of the biggest limitation for the code coverage. Second thing, the concurrency is a special case of the fundamental aspect that the code coverage is not time sensitive, right? That's what it is. So concurrency is something happening at the same time. And the third point is the, with respect to time, is the temporal sequence. That is, whether certain set of events have happened in certain order or a certain sequence is not something that the code coverage metric can tell you, right? So for example, if I wanted an interrupt at that point of time, whether the certain the outstanding interrupt was already present before the occurrence of an error, right? If I want to find out if such a scenario has happened, I cannot do that with the help of only the code coverage. Okay, that's not possible. And the other thing is that the implementation may not be implementing the requirements correctly. Okay, and that is not something that your code coverage metric can tell you. Now this is one point we need to understand slightly clearly, because many times the engineers tend to confuse between checks and coverage. Okay, checks is different, coverage is different. Okay, checks tells whether the operation is taking place as per the requirement specification, and the coverage tells us whether that particular operation or the feature has been exercised, and they are two independent things. And what happens, why do we say that then, if the checking is not responsibility of the coverage, then why are we saying that the implementation may not be implementing requirements correctly? If correctness is the responsibility of checks, not the responsibility of coverage, right? Then why are we combining this? So let's understand one fine point over here that will tell us why we are making this particular point. So what happens is, in the code coverage, if I have achieved a code coverage, that doesn't mean it is bug free. Okay, and why do we say that is that when we provide any stimulus and when certain code gets executed, right, the results get created, and that results may have certain propagation delay that it needs to go through some stages to reach the test bench, right, and that is where they get checked. And but as soon as I have applied the stimulus, the code coverage is telling me that it has been covered. Okay, so it has sampled it. It has sampled and said it has been covered. Now it is not waiting till the effects have reached the test bench. Okay, as soon as it has exercised, it is registering in its database that this particular line has executed, or this particular condition has executed, or this particular state transition has happened. But it's not waiting for its effect to reach to test bench, wherein the test bench is going to tell that this particular thing is correct or wrong. It's not waiting for that, right? And sometimes I'm not saying that the test bench will not eventually flag a error, right, and then we exclude this particular coverage from the overall database. I'm not saying that that won't happen, but it is essentially not sampling something after it has been qualified, right? It is sampling before, and hence there exists a small possibility that it could lead to it could lead to miss false positive type of a coverage, right? So that is the main point, that the point of sampling the coverage is not in user control. So if it's something just gets exercised and then it just gets sampled, whereas when you contrast that with the functional coverage, which we will look at it eventually, that in the functional coverage we have control on the point of when do we sample the coverage, right? So now what can happen is, let's say even if let's say I'm missing a check in the test bench, and I say that when I issue some stimulus, something when it shows up at the output boundary from the DUT to test bench is when I'm sampling, and if that doesn't show up at all, then even though check is missing, I am not sampling the coverage also. There's some level of protection. I'm not saying it's 100% protection, there's some level of protection. But in case of code coverage, what happens is there is not even that protection, that as soon as I've applied stimulus, it has sampled it. So because of lack of control on the sampling point of registering the metric, the code coverage is more prone, I should say relatively more prone. Both the metrics are prone to certain set of false positive biases that we cannot totally eliminate, but we can say that code coverage is relatively more prone to such biases compared to the functional or the assertion based coverage, wherein we have the sampling point under the control. And of course we have it under control. Now it also goes with the additional caveat that the implementer of such metric needs to make sure that he is using the sampling point to sample it at correct point. Now if somebody doesn't do that, then even though you have the sampling point under your control, you could still end up having the false positive coverage. That cannot be prevented, but the mechanism is provided, there is better hooks provided in case of the assertion and functional coverage to sample the coverage at more appropriate point compared to the code coverage. So that is the point that you need to keep it in mind when you contrast the code coverage and the functional coverage, plus why we should not only rely on code coverage to say that design has met the functionality. Okay, let's just summarize the differences that we discussed. So between the code coverage and functional coverage, right? So first is code coverage is automatically generated by the simulator based on the design RTL code, whereas functional coverage has to be, it has to be manually defined, that you need to really define a coverage plan, and then you need to implement it using the cover group or the assertions based on the requirement specifications, right? So that is what you need to do when you do the functional coverage. And the code coverage does not cover requirement specifications because it's only based on a particular design implementation, and whereas the functional coverage is primarily targeting the requirement specification, that you really take requirement specification, go through each of the sections, subsections, and look at each of the lines of the requirement specification, and then you identify, in order to say that particular line of the requirement has been covered, what do we need to how do we need to really express that in the form of a cover group, right? So that is something that you do when you implement the functional coverage. And the main the like a technical deficiency for the code coverage is the its inability to capture the temporal sequence and concurrency. That is, it cannot capture time, right? So concurrency is some things happening at the same time, and temporal sequence is things happening one after another, right? So it cannot capture both of them. Whereas when you do the functional coverage, either based on cover group or if you do it based on the assertion as well, it can cover temporal sequence and it can cover the concurrency, right? So that is what is the advantage, the main technical advantage for the functional coverage in terms of its capabilities. Then the other way to say the same thing, code coverage gets generated implicitly, whereas the functional coverage has to be explicitly created. And even the coverage sampling is implicit in the case of coverage. When we say something covered, it's implicitly sampled in case of code coverage, whereas in case of functional coverage, that coverage sampling is done explicitly. So there are key differences between the functional coverage and the code coverage. Okay, so anything that we can generate without putting any additional effort, right? That is something that always becomes popular. So code coverage is no exception. So due to its implement or automatic nature, right, it's generally the first choice to identify the deficiencies in the stimulus. And typically all coverage metrics are tracked and generated by the verification teams, and they are also closed by verification teams, so that is the responsibility for the verification team. But for the code coverage, what happens is, since it's based on the design and the verification team may not have like a very in-depth design understanding, that they may have overall microarchitectural level understanding, but why certain conditions is coded certain way, or why certain design is the way it is, those aspects they may not have full clarity. So what happens with respect to code coverage is, generally whenever you have code coverage holes, a verification team approaches the design team, and then design team helps them to translate a verification hole to what exactly stimulus that needs to be generated in the test bench, right? So they help do that mapping, and then based on that mapping, again the verification team updates the test bench if required, or runs some specific tests, tunes them to target that area and to exercise it. One of the big challenge with the code coverage is the total volume of data that gets generated. It's very huge. Okay, it's quite huge, especially for the complex designs. It's a lot of data, and there are parts that of the code that cannot be covered as part of functional verification. There could be few, it's not like, for example, there could be few DFT related hooks that are present within the design, so that may not be possible to cover using the functional verification. So those needs to be excluded. And not only those, but there are certain areas of the valid design itself, those cannot be exercised within the timelines that have been allocated, and they have been found to be that they are not very critical. So those generally get manually waived off, because ultimately you want to make sure that at the point of sign off you have achieved 100%, right? And the way to achieve 100% is whatever that can either be not covered within the purview of the functional verification, and whatever that you cannot cover because that is not required, or that is something that the design team thinks that it's a low risk item which doesn't need to be really covered, they are all waived off. So lot of the exclusions get created for the code coverage, which are then applied to the report, which enhances the total results that are accomplished by the code coverage. And that is what you rely on to do the sign off. And one of the challenges that's associated with the code coverage management even till today is managing these exclusions. So you create these exclusions, let's say particular expression has been not covered, and you say that that particular expression now is excluded manually. But then what happens is there are revisions of RTL that keep happening, and then that particular expression gets updated, or that moves to a different line, and then again you need to go ahead and do this process of manually mapping it back and creating the exclusion. So that process is a very is very manually intensive and challenging. To identify exclusions, that's the first step, and then manage them over a series of revisions. So that's something that's a hard or a challenging aspect about the code coverage. Okay, there are different types of code coverage that are present. So let's look at them. So first we have the toggle coverage. So toggle coverage tells us number of times each bit of register or wire has toggled. Okay, and it reports both 0 to 1 transition as well as 1 to 0 transition, and number of times it has taken place. And IP verification, when you do the verification at IP level, you tend to focus both on the register as well as the port toggle coverage. But when you do the SOC verification, you typically tend to target only the toggle. Okay, so you tend to target the toggle for only the port level signal, because at the SOC level, your main focus is how these pre-verified IPs are interacting together. That is what is your primary focus when you go to the SOC verification, because all the, like, let's say I have a UART, I have a SPI, I have a USB, I have PCIe. Each of these IPs have been either pre-verified or bought from some IP vendor. So from a verification team point of view, it's a pre-verified IP. Right now, when we do the SOC, what we are ultimately trying to do is we are trying to connect all of these blocks together. So the only additional logic that's really coming in is the way we have connected these things together and how we are generating the clocks and resets, and then some low power management. So there's only a specific part of the new functionality that comes in as a part of SOC. Rest of it is a pre-verified functionality. So connectivity is one of the major new things that comes in the form of SOC, and SOC verification predominantly focuses on the interconnect coverage, and one of the metric that is used to measure that is the toggle coverage. So between two IP blocks that you are connecting at the SOC top level, the toggle coverage between those IPs, the toggle coverage of the ports that are connecting those two IPs is one of the important metric that gets used. Then line coverage is a second metric. So line coverage helps us measure which lines of source code has been executed during the simulation, and dead code or unused code can be identified with the help of line coverage. So what happens is, over a period of time, a particular IP might evolve in terms of its feature, and certain features might get deprecated and removed from the test bench, but they might be left out within the design. Right, so in those cases, when we look at the code coverage report, we can identify that this is a dead code or is like unused code, and that can be again removed from the design. Sometimes it could lead to savings of the area as well. And then IP verification typically targets the line coverage. So toggle coverage is the only metric that's used by both the IP as well as SOC verification, whereas the rest of code coverage metrics, they are mainly targeting the IP level verification, because within, when you do the IP level verification, you tend to go very deep inside the IP, but when you do SOC verification, you stay at the peripheries of the IP. That is the distinction. So branch coverage is the Boolean expression used in your control structure, such as if, case, etc. It checks whether it has been evaluated both true or false. Again, it's targeted. The target is the IP verification that targets the branch coverage, because very internal aspect of the design IP. And then you have the expression coverage and focused expression coverage. So it's also very important part of the code coverage. The expression coverage is also referred as condition coverage, and used to determine if each condition is evaluated both to true and false. Right. So in case of branch, we were just thinking that whether the like if and else both have been executed, whereas here it's looking at the expression, and then if that particular expression is made up of multiple logical expressions, then whether each one of them have become true or false. Right, so that is something that's considered when you do the expression coverage. Right, and then it reports each Boolean condition independent of each other. Right, so if I have made up of multiple things, it reports them independently. So that way you will come to know that like if I had A or B, then whether sometimes A had become true, sometimes B had become true. Because in case of branch coverage, what happens if A or B both are true, then also it will cover. If A is true, it will cover. B is true, it will cover, right? So that way we don't know. But whereas when you look at the expression coverage, each of the independent Boolean expression, whether it had taken both the true or false values, you will come to know. And there's also this focused expression coverage, which is a special variant of the expression coverage. Here what happens is, ultimately, as I talked about, if I have A or B type of an expression, right, then and it's finally contributing to something. Let's say C is equal to A or B, if I'm saying, then whether the C has become true because of A only and whether the C has become true because of B only is a focused expression. So I'm focusing only on A and I'm focusing only on B. So because if A and B both are 1, and then if I do A or B, then there is no way we can figure out like whether the C has become true because of only A and because of only B, right? So in the focused expression coverage, it will make sure that the final condition has evaluated because of each individual expression, right? So it's a stronger condition coverage, and each condition in decision has been shown to independently affect the decision outcome by varying just that condition while holding fixed on all other conditions, right? So that's what the focused expression coverage will do. It's very hard to kind of close the complete FEC coverage in case of code coverage. And most of the time, if it's like a safety critical application, typically the automotive type of an applications, right, they tend to pay a lot of attention to the FEC coverage. And the last component of the code coverage is the finite state machine coverage. So simulators, they can identify FSM structures, right, within your RTL code. They will be able to identify that, yeah, there is a state, and then based on the state you are generating next state, and then the output conditions, all that it will be able to identify. So it will identify the FSM structures. And once it has identified an FSM structure, of course, there are certain coding guidelines that the design needs to follow to facilitate this process. But but once you have followed that coding guidelines, and the FSMs get automatically detected, and then the coverage for them gets reported, and then the FSM coverage is all automatically extracted. And this is also like the expression coverage or a toggle coverage. This finite state machine coverage is also one of the important dimensions of the code coverage. And typically the following information gets reported, like for example, whether each of the state has been covered, and number of times each of the state that has been identified is entered, and number of times transitions that have taken place, right? It will identify all possible transitions, and then it will check which of the transitions have been covered and how many times it has been able to cover. So all of it will be able to identify and share you the report in the form of a code coverage report. Okay, so we have looked at the code coverage. Now let's look at the functional coverage. So functional coverage focuses on design from implementation completeness from the requirement specification point of view, right? Whether all the requirements that have been defined are all of those implemented in the design or not is the focus of the functional coverage. And then when we say requirement specifications, the requirement specifications can be in the form of a standard or like a proprietary specification. When we say standard specifications, it could be like, PCI SIG providing PCIe specification, or USB.org providing USB specification, or MIPI providing, like let's say Unipro for a flash storage type of a requirements. So these are all standard body requirement specifications, or it could be like a proprietary specifications, like an AMD or NVIDIA implementing their own GPUs, right? So those are all, there's no standard body governing how the GPU needs to be implemented. So those are all proprietary specifications, but there is a requirements, right? So either from a standard body or within the company in the form of proprietary, there is a requirement specification. And the goal of functional coverage is the completeness of the design from the requirement specification point of view, right? That's what the functional coverage is looking at. And so generally when you implement functional coverage, you can do both sort of like a black box as well as white box. If you purely focus it from the requirement specification point of view, then it's a black box functional coverage, that you are not looking internally how it's implemented. As we even talked about in the prior in this particular session, that a requirement can be met with a different microarchitectures, right? So but sometimes the verification teams also tend to look at microarchitecture and make sure that they do write some microarchitectural functional coverage as well. So that's sort of like a white box functional coverage. So both of them are targeted, but predominantly verification team focuses on the black box functional coverage, which is adhering to the completeness of the requirement specification point of view. They in fact go through all the requirement specifications, as we talked about, pick each section, pick each line, and then in order to make sure that design has implemented that particular line, what is the stimulus that we need to cover and what responses do we need to cover. So you look at it from that point of view and define your coverage plan and implement it, right? So and once you have done that, it should help you answer the questions like, have all requirement specifications have been implemented, right? As we talked about, that's what you should be able to answer once you have the functional coverage. And then have all the second thing that you want to check is, have all the requirement specifications have been exercised in all possible combinations, right? So that is what you want to check, whether have all of them have been implemented and all of them have been exercised. Exercise meaning that you are giving some stimulus and you are getting back some response, that's expected response. Of course the checking is done by the test bench, but still you make sure you sample it, that only after the response has come, at least that level of check happens through the functional coverage. And the functional coverage has gained prominence with the predominantly with the rise of the constrained random verification, because in the constrained random verification what happens is the nature of stimulus is random. So although you have defined the constraint random to target the critical space in your design, but there is no guarantee that it is really going to do that. And so whatever is extremely critical for you, what you do is not only you design it, but you also define the functional coverage plan around that and implement it in a very detailed fashion, so that it has really gotten exercised. So that is why the functional coverage has become important with the randoms, because since randoms there is no 100% guarantee that it is going to really do certain scenarios. So if that scenario is important, you as well define the functional cover point and then make sure that it has been exercised. Okay, so as we have seen, functional coverage is an explicit metric and it's not automatically generated. And these steps are typically followed, that you define the functional coverage in the form of a coverage plan initially by referencing either your requirement specification for sure, and then additionally, if on need basis, even the microarchitecture based white box functional coverage plan can be defined for the completeness. And then you implement that particular coverage model. We will briefly look into how to implement it, like what's the overall idea of implementing the functional coverage model, and then when we look at some of the project execution, we'll look at more concrete way of doing it. And then once you have implemented a functional coverage model, you need to integrate that model into the test bench and then exercise the tests to see whether the functional coverage is getting hit. And typically your functional coverage plan, as we talked about, are specification indexed, so that if somebody says, hey, you know, did we really cover this particular specification section 12.2.2, then we should be able to go into the our coverage plan and be able to tell that, yeah, this particular section we have targeted these cover points, and then we can look at it, right? So you generally do a specification indexed coverage plan, and this whole process that I'm talking about is all done manually. And then there is, again, when anything that we do manually, there is a possibility that something could get missed, right? Even a specification section could get missed, or a particular line in the specification could get interpreted in a different way than what it is. Those all things always exist, and hence we say that the functional coverage is just as good as its definition, right? So somebody could do a very great job of defining a functional coverage plan, and somebody could do an extremely poor job of defining a coverage plan, and hence our coverage model is only as good as whatever the plan that has been defined. So everything has its own pros and cons. I am bringing those things out over here. Then there also exists a possibility, since, like, for example, the code coverage gets implicitly generated, but we have to now implement the functional coverage model. Implementation means we need to write additional code, not only to model the coverage, to integrate it, and then sometimes we'll have to write additional auxiliary code to store something till a particular point, and then we need to sample it and use it for the functional coverage. So whenever we write that additional auxiliary code, there is a possibility that there can be bugs within that particular code. So that again causes a possibility of either a false positive or a false negative type of a coverage, since we again don't have a test bench to test the functional coverage model itself, right? So those are some of the challenges associated with the functional coverage. As we talked about challenges associated with the code coverage, like the exclusion management, for example, similar way, these are some of the challenges associated with the functional coverage as well. Nothing is perfect. We have to utilize multiple things and then do a sort of do a checking of one thing based on another. That concept that we have talked about, like a reference model concept. The reference model concept is not limited only to implementation of scoreboard. In verification, you always tend to validate, okay, this component is saying this thing, this component is saying something. Are both of them same, right? So that manual diligence of making sure that things are consistent across the environment is not just it's not just done with the code, right? That the verification engineer, it's a responsibility of verification engineer also to make sure that you look at some information over here, you look at some information while you're debugging, you discover some information. We should not confine that, oh, I have discovered this information and it's left there only. It's not like that. You discovered that information. Now when you're looking at a coverage model, if it is that not in line with that particular information, you need to say it out that, hey, I had looked at this, it was behaving like this, while this functional coverage model is behaving like this. Why is this, right? So that type of cross referencing and cross checking with referencing one thing to another thing, right, is a very key part of the overall process of functional verification, right? So we need to have certain level of redundancies, and we need to keep checking through multiple eyes to make sure that finally it's all done correctly. Okay, so this is a very high level block diagram of a typical functional coverage model. So what happens is a coverage model is a combination of two things. One is a auxiliary logic and another is the functional coverage. Okay, the functional coverage itself could be implemented using the two constructs that we have talked about. It could be like a cover group construct that we could be using. So in the subsequent session, we will see the cover group construct, and we have already seen the cover property, right? So using these two constructs, you implement the functional coverage, and the auxiliary logic itself could contain system Verilog behavioral code, the one that we have discussed in the context of both procedural and object-oriented programming. So it could be that code, or it could be an RTL type of a code as well, because if you are using a cover property type of an construct like a concurrent assertion, you need some way to model. You are actually capturing a waveform, and then you need a code to generate waveform, and RTL is best suited to do that. So you could have an RTL type of an auxiliary code which creates this additional information that you want to rely on for doing your property based coverage, and then you need some code for integrating the coverage with the test bench. It could be that I might be passing some interfaces, I might be passing some transactions, or I might be passing some global object containing state information. All that plumbing has to be done. So that's the additional code for the integration. So these are all part of your auxiliary logic. So let's look at the block diagram. So you have a DUT and you have the test bench, and DUT and test bench are interacting with each other. And then what can happen is the information to our coverage model flows through this auxiliary logic. And the job of auxiliary logic is, what happens is, sometimes when you want to sample some information, maybe the information that you want to sample may not be available in the way you want to sample. That is one problem. Second problem, there could be multiple sources of information might be coming in together, and you want to massage them and create it in such a way that you want to sample it together. So I might have to wait for certain things to happen. So all those things, right, any transformation, waiting, all those things become part of your auxiliary logic, because these constructs by themselves, as you have already seen, for example, property based property or the concurrent assertion implementation, except for using few local variables, there is not enough support for creating any additional logic, and a lot of times you need additional logic to implement the intent of the coverage plan. So in such cases, what you need to do is you need to rely on the additional logic that is implemented outside. Okay, so in those cases you implement this particular auxiliary logic. So what happens is, if sometimes you can directly sample the information, then this path from test bench to RTL could be just a pass through, but many times you might be doing the massaging. So the block containing the auxiliary logic is shown, so you might be taking certain information from the DUT, and you might be taking certain transactions, state information from the test bench, and doing some sort of massaging or passing them as is, and then you pass it to like a cover group based function coverage model, and then the same thing could be, again, the massaged information could be passed to property coverage based functional coverage model. So so this is a container for a functional, the property based. It could be a module, it could be a checker. There's a checker is the equivalent to sort of always equivalent to a module. We will discuss about the checker construct briefly in the next session, or it could be module containing that, or it could be a program block containing that. And cover groups also can be placed within the class based. Typically it will be a class based construct, and it could be placed also within the interface construct, for depending on if you want to really cover the interface within the interface construct itself. Interface functional coverage can be done within the interface itself, so you could be implementing cover groups within the interface construct. So depending on the type of requirement, the cover group could be placed at different containers, and then you connect those containers to your auxiliary logic, and then take the information. And then when you bring in the information, it's two types of information for the cover group. One is the actual information that needs to be covered. Let's say a transaction type needs to be covered, and then when exactly does it needs to be covered, right? So those two things become important. Okay, so when to sample, that's one information, and what to sample. So both of them will be provided by the auxiliary logic, and that's consumed by your coverage constructs. So that's the overall idea of the block diagram for a coverage model. So once you have implemented the coverage model, and then you have the implicit coverage generation flow in place, which is nothing but enabling few options in the simulator, and then you have implemented a functional coverage model and integrated into the test bench, and you are able to create the matrix that you are able to look at how the verification is progressing. Then there comes in the regression debug flow, as we have seen before, there comes a point where we need to march towards sign off, right, wherein you want to tape out and create a chip. So how do you go about that? How do you go about the coverage closure flow? So first step is that you enable the overall or the specific code coverage metrics, and then you could be doing a targeted thing, and then you run the regressions and collect individual test coverage database. So what happens is like a waveform. So you guys have been, like, for example, generating a waveform database like an FSDB or a VCD, and opening them up and looking at the waveforms per test basis, right? So similar to that, in the command line, which is the test command line, you can enable additional options to the simulator to dump the coverage information. Okay, so it will dump the coverage information per test. So as soon as the test run completes, it would dump a database per test. You can give a name to that database. Generally what you do is a test name and underscore the seed name. So we have talked about it, right? So in the context of constraints, we have talked about that for any given test, depending on the level of randomization that it contains, you run multiple seeds of that particular test. So what you do is you use the test name underscore the seed name, which gives you a unique name, because you are running the same test with multiple seeds. So you use the test name with the seed name to create a unique name for a coverage database for every command line that you're running. So when you run it, that particular database gets dumped. So it could be like, let's say test one, I'm running it with 2 seeds. So I will say test one underscore seed number could be any random number. So I'll say test one underscore 127 dot whatever VDB, and then I'm running another same test one with a different seed. I'm saying test one underscore 1028.vdb. So those 127 and 1028 are the seed number that I have provided. So those two database files get generated when you run the regression of those two tests, and then the tool provides the ability to merge those databases to generate a collective coverage metric. So individually it provides what that particular test has covered, and then what you need to do is overall you want to look at, you run this full set of group of tests, and across all those tests am I able to meet my coverage requirements. That's what you are trying to look at, right? So what you do, you take all those coverage database files that have been individually generated and make sure that you pick up the tests that have only passed, right? You don't want to merge the coverage database from the failing test. This is a very important point, right? So, and all these mechanisms are typically, every company has their own scripts to do these things. So you take all the passing coverage databases and then merge them together, and then along with that, as we discussed in the context of code coverage, there could be something that we want to exclude, right? So we might want to exclude some DFT structures, or we have decided something is not critical, low priority, we are not going to cover that, or covering this doesn't matter. So all those things, we have created an exclusion file, okay, that's simulator specific again. So that exclusion file, so we take all passing test coverage databases, we take the exclusions and put them together and merge them. The simulators provide commands to do this, so we merge them and then we generate the final coverage report. Okay, so that final coverage report across all our regressions with all our exclusions, what is the final value of the code coverage, what is the final value of the function coverage, it will be able to tell that. And from that number you can keep on clicking. So typically they provide either within the HTML you can view it, or HTML reports that can be viewed within the browser, or you can open the GUIs of the simulators, right? And then within the GUI you can navigate from the top level number, you can keep on traversing down to the hierarchy, saying, oh, this is the code coverage. Okay, so I want to look at a branch coverage, I want to look at a the line coverage. You can go to there, and then per module level what are those metric, and then you go deeper into another, like that module might be instancing lower leaf level modules. You can go to those leaf level modules and look at that module level what are these n number of metrics, right? The code coverage metrics I'm talking about, because code coverage is the implementation specific, so it follows the RTL structure from your top level module to the modules that are present within that. It will show you at that particular module level what's the line coverage, branch coverage, your expression coverage, FEC coverage, everything. It will show you the overall number as well as the breakup, and then you can click on those numbers and it will further show you within that particular module. Like for example, if it had 10 lines, 4 lines were covered, which are the 6 lines that are not covered, it will show it in some red color or something, and thereby you figure out that these 6 lines within this particular hierarchy of the RTL doesn't have the code coverage. Similarly, in the functional coverage level, you can click on that and it will expand to the different number of cover groups. Within the cover groups you can look at what are the different cover points, and within the cover points or you can have crosses, which of the bins that are not hit, they will again be reporting it. And then with those information you analyze those reports and then identify the reason. If it's a code coverage, you obviously talk to the design team to understand what you need to be doing in the test bench as to what type of stimulus do you need to create to exercise that uncovered area. And if it is a functional coverage, obviously you have defined it to certain requirements. You are expected to know that what changes do we need to do in the stimulus. Do we need to increase the distribution for certain stimulus generation, or are we missing something, or do we need to create some corner case by adding some additional weight and orchestrating across interfaces to make that particular scenario happen. All those things you figure it out by analyzing the coverage reports, and based on that analysis you figure out, okay, we probably need to add new tests, new directed tests we need to add, or new variables we may have to add to the randomization, or we want to create a variance, right? That is saying that I will pass a command line argument to control the size. Okay, let's say a transaction size, the highest size transactions, they are not enough, so I will constrain, or I will add a command line argument which will override the soft constraint and generate that specific area, or I'll disable a particular soft constraint to expand the scope of stimulus. So you will do those things that we have talked about in the previous also, how you can expand the constraints or you can override constraints to make it more pointed. Either you make it more pointed or you expand the scope or add new tests. So one of these things you do, and once you did that, again you go through this entire process, right? So you bring that back and then enable disable certain metrics if you want, then again run new set of regressions with a new tests with a new flavors, and go through the process of merging the coverage databases. And then based on this analysis you might have added additional exclusions, so those all lead to the boosting of the functional coverage number. So you might be at 86 and then it will become 91%, and then you keep on doing that. After 91 it might become 93, 95, and so on and so forth, right? So it's an iterative process with few iterations depending on the complexity. You achieve the convergence, right? So, and once you have achieved the convergence, it may not always be, as we have discussed about it, that it may not naturally hit everything. Ultimately you might add few exclusions after discussing with the entire team, and once you have the common consensus or the agreement, you add those exclusions and you write reasons for those exclusions. That is very important, because just adding exclusion is not sufficient. You have to capture why we have added that particular exclusion, and then your coverage becomes 100%. So you say that now from the coverage metric point of view we are signing off on the design. There are different metrics, coverage is one of those metrics, so we are saying both from the coverage, code coverage metric point of view, functional coverage metric point of view, since it has achieved the 100% in a judged way, we are signing off on this particular design. You say that, and then it moves to the next step. So that's how the code coverage flow works. Okay, so this concludes the session on overview of the coverage metric. So we have looked at the different types of the coverage metric. We have looked at the code coverage, and again we have looked at within the code coverage we have again different types of code coverage that are possible. We have the toggle coverage, we have branch coverage, and then we have line coverage, we have expression coverage, we have a focused expression coverage, we have FSM coverage. So we have these different flavors of the code coverage, and all of it gets generated implicitly. And we have looked at that the toggle coverage is the only code coverage that gets even utilized at the SOC level, because at SOC we are focused on the interconnectivity verification, because that's the only major new logic that gets introduced in the SOC. Rest of the IPs are anyway already pre-verified, and we looked at how there are some limitations with respect to code coverage that exists. So we know that the time is the weakness for the code coverage. It cannot understand time, so which manifests itself into not being able to understand the concurrency, that where two things happening at the same time, or the temporal sequence where things happen one after another with some time predefined time gaps, right? So those things cannot be captured by the code coverage, and hence you need to go after the functional coverage. And while the code coverage focuses from the design point of view, functional coverage focuses from the requirements and the microarchitecture point of view, predominantly from the requirements point of view. So the functional coverage needs to be implemented, and you have two constructs available to implement the functional coverage. You can use the cover group construct, which we are going to discuss subsequently, and we have already looked at assertion based temporal functional coverage, that sequence coverage that you can do, which will provide you the functional coverage. And we have looked at the how to structure the functional coverage model with the help of auxiliary logic, and along with your cover group and the assertion based coverage, and how your auxiliary logic helps you to massage the information coming in from the DUT as well as from the test bench to provide two key sets of information: when to sample, what to sample. It will provide those two information which is consumed by your cover group or assertion based coverage models, and they provide you those metrics. And we looked at finally how the overall flow works, that you run the regressions, and per test the coverage database gets dumped. You merge the coverage database for only the passing tests, and then you take into account any exclusions, approved exclusions that have been accepted in the team, and then analyze the overall final coverage report and get the judged code coverage metric to 100%, and then sign off from the point of view of either the code coverage or the functional coverage. That doesn't mean everything is over. It just means that from those metrics point of view it is signed off. There are different metrics. We need to look at multiple metrics to do the sign off, but from the coverage point of view, that you can say once these metrics are met, they're judged 100% values, you can sign off on them. So yeah, I hope this session gives you the fundamentals about the coverage metric. We have discussed about the functional coverage through the cover group construct in the part of this session, so that lays the foundation. Next we will look into the system Verilog cover group construct itself, which we have not looked at. And okay, so yeah, thank you for listening.